Okay, good morning, everyone. Thank you, Abby, for the introduction. So let me give you a bit of context first. So what is MPC? What is this all about? Well, in MPC, we try to solve the following problem. So in MPC, we have several parties, 2, 3. In this case, I'm just showing 4. And they want to compute a function in such a way that only the output of this function is revealed to the parties and nothing about the input is revealed. So this can be done, for example, with a trusted party if each one of the 4 parties send their input, and then the trusted party promises only to reveal the output. So that's, of course, doable. But as privacy-aware people, we would like to remove trusted parties from the world. And then in MPC, what we want to do instead is to have like a similar behavior, but involving only point-to-point communication between the parties. OK, so MPC is quite an old problem. It comes like from the 80s. And if you want to compute circuits over F2, then there are some approaches to do that. For example, garbage circuits, which is one of the first solutions to this, or BMR, which is the generalization to multiple parties. You also have GMW and so on. And there are many more modern ones, because these are actually quite old. If you want to compute a circuit actually over Fp, over the field of integers modulo P, where P is a prime, you have other set of solutions, like Vedosa, VGW, Speeds, Mascot, and also many more. But when you want to focus on computing over on a circuit that is integers modulo a number that is not a prime, for example, 2 to the k, 2 to the some number, then there are not so many solutions. Like there are some. There is, for example, ABY tree, or there is a ShareMind, and also like a compiler from Crypto 18 presented by Downguard et al. But for the dishonest majority setting and active security specifically, there is only one solution, which is this work called Speeds to K by Kramer et al. At Crypto 18. Now, why is there is only one when there are so many in the other setting? Well, the ring is actually quite a complex structure. So a field is a ring, but not every ring is a field. Sorry, a field is a ring, but not every ring is a field. Yeah. So it's because the rings may have elements that are not invertible, for example, and there are like a lot of weird things going on, and that complicates the design of protocols. And if it's so hard, then why would you actually want to compute on them? Well, there should be some benefits on computing over these rings. And like the first one that comes to mind is, well, set k to be 64 or k to be 32. And now you're computing on native data types. And that's amazing, because then everything should be at least intuitively faster, like when it comes to computation. And also, like our programs already, if you write a program in C or in Java or whatever the programming language, you're probably already aware of overflows modulo 2 to the 64. You're already programming taking this into account. So there should be like, at least intuitively, like an easier compilation from these programs to MPC programs. And also, something that we do a lot of in MPC, and for example, that can be seen in the work of ABY3, is that you have to convert a lot from arithmetic sharings to binary sharings. Because some things are cool to do with arithmetic shares, like additions, multiplications, and so on. But when it comes like to flow control, having like if statements and so on, you need to go at the level of bits. And then it becomes a bit hard. So if you're working modulo powers of 2, it makes sense, at least again intuitively, that this is like more compatible with binary computation. So what do we do in this work? Well, in this work, we develop new primitives for this type of computation. So we expand the Speeds to K protocol with a lot of primitives for example, secure truncation, comparison, equality check, and so on. This is super important because the Speeds to K protocol only comes with basic addition and multiplication. And of course, in practice, if you want to use one of these protocols, you would like to have much more primitives than just that. We also implement the protocol. We provide an implementation in Fresco, which is a Java framework for MPC. And the cool thing about this framework is that it already has speeds implemented in it, and also Mascot, which are protocols that work over field. So by implementing our protocol there, we can get like a clear comparison between the two that is fair. So like the results are actually very meaningful. And the main point is that we indeed get some improvements with respect to protocols over fields. We'll discuss that later on in more detail. And now that we have, like, of course, all this set of primitives and all this protocol and so on, what do we use it for? We just tried, let's apply it to secure machine learning. So we applied our protocol to the secure evaluation of decision trees and also support vector machines. And I'm going to discuss that later on at the end of the talk. So we have in order to present our results, of course, we need to talk a little bit about the underlying protocol that we base our work on. And this is SPITS2K. So what is SPITS2K about? It's very similar to SPITS. And the core feature of any of these protocols for this honest majority or any secret sharing based protocol is what we call like secret sharing scheme or like authenticated secret sharing. So basically you have like a way of sharing your data among the parties, and then you go through the circuit maintaining the invariant of the secret sharing, and then at the end you reveal the result. And this is like a basic layout that many protocols follow. And in SPITS2K, the secret sharing scheme works as follows. So to share X, which is an integer modulo 2 to the K, and we denote this by this, we proceed as follows. So each party is going to have like an additive share of X. But it's not really an additive share of X. It's an additive share of X prime. This notation, by the way, means that these two things are congruent modulo 2 to the number that is here. So S is going to be the security parameter, and each party is going to have an additive share of X prime, where X prime is not X, but is congruent to X modulo the lower K bits. So that's very similar to SPITS, and SPITS is just the same, except that here instead of X prime, you have X. Now, so all parties have additive shares, but they also have additive shares of a key, which is going to be global for the whole computation of the circuit, and also random. And they also have additive shares of a MAC of X prime, where the MAC is alpha, the key, times X prime. So this is the secret sharing scheme, again, very similar to the one used in other protocols. And now, once you have a secret sharing scheme, going from there to a protocol is actually like, this is the template that has been used for a lot of time, which is you first need to distribute your inputs. So this you do just by masking your own input with a random value that you know, and also the parties have shares of this random value. Did you preprocess it somehow? I'm going to get into the details of the preprocessing. And then you broadcast this value, and everybody can undo the mask with their shares. So now everybody has shares of the input. Addition gates are computed locally because the secret sharing scheme is additively homomorphic. And for multiplication gates, we have this nice trick by Bieber et al. About using multiplication triples, which is you preprocess a triple where C is the product of A and B, and then you can actually open the difference of X and A, the difference of Y and B, and do this, take this linear combination, and you can check that indeed this gives you X shares of XY. So very standard approach to get MPC. Now, again, only addition and multiplication, we would like to have more protocols on top of it. So let me introduce some of the primitives that we introduced. So this is sort of the roadmap, or the map like, of the things that we introduced in this work. I would like to throw your attention in this particular column. So this is the core primitives that we need for the protocol to work at all. So we have the normal triples that we generate using SPITS2K. There's nothing new yet. We also have triples that are not C2 to the K, but C2, so binary triples. Also obtainable with SPITS2K, but we show one optimization about how to get them with another type of triples. I'm not going to discuss this in the talk. But what we introduce in this work is the generation of random bits. So share values that you know that the underlying value is either 0 or 1, nothing else. So that turns out to be a very important primitive, as I hopefully will convince you later on. And we also have shares conversions from binary shares to arithmetic shares and back. Now, in this column, we can see sort of the primitives that we introduced. So we have truncation, which is very important for fixed point arithmetic, and we also have bit decomposition. So you have shares of a value, and you want to get shares of the bits. We have equality check, the extraction of the most significant bit, which is equivalent to comparing two numbers in equality. We have also another inequality, but it's like bitwise inequality, and then finally obtaining the carry bit of an addition. A lot of primitives for being able to get more applications for this type of protocols. Indeed, we showed that you can apply these guys and use them for SVMs, for the evaluation of support vector machines, and also for decision trees. Now, of course, due to time limitations, I won't be able to cover them all, so I'm actually going to focus on the generation of random bits, the share conversions, the bit decomposition, and then finally talk a little bit about the benchmarks on the last on the applications. So let's begin with generation of random bits. Super important primitive again. Like once you get this primitive to work, pretty much all the other primitives follows relatively directly from the generation of bits. So this is not the actual protocol. This is the ideal protocol. This is how you would like this protocol to look like, or more precisely, how it has been done before. So you are working over rings, and you say, let's try the same thing over fields and see if it works. So over fields, it looks like this. First, you sample a random element, and then you square it. And you open the square. Intuitively, like the square gets rid of the sign, so you lost all the information about the sign. So therefore, it's OK to open the square. And the sign is going to be like our bit. So you open A, and then you let C be some square root of A. So let's say the negative one or the positive one, any one. It doesn't, any of them. It doesn't really matter. And then you compute D to be C inverse times R. So if you square this guy here, it gives you A times R squared, sorry, A inverse times R squared, so A inverse times A, which is 1. So D is a square root of 1, and we all know that square roots of 1 are only minus 1 or 1. So now D is a random element, which is basically the sign of R. That's pretty much what it is. So it's either minus 1 or plus 1, and then you want to map it to either 0 or 1. So this is just a simple affine transformation. You add 1, and then you get 0 or 2, and then you divide by 2 to get 0 or 1. And this should be a random bit. So this should work, but unfortunately, it does not work, and hopefully you already spotted maybe some places at which it doesn't work. Over rings, it doesn't work in these places. So first of all, let's take the inverse of C and multiply by R. Well, who guarantees us that C is invertible? Because over rings, we may have some elements that are actually not invertible at all. Specifically over this ring, even elements are not invertible. So this step requires some care. Also, like if D is a random square root of 1, then it has to be either minus 1 or plus 1. That's also not true over rings. So there are some polynomials that have many more roots than their degree. So in this case, this is not necessarily true. And finally, like when you divide by 2 here, like dividing by 2 is again not trivial over a ring. So what do we do? How do we overcome these issues? Well, 3 main things. So first of all, we're going to increase the modulo a bit. We're going to sample R modulo 2 to the k plus 2, and hopefully in a moment you'll see why this is useful. We're also going to ensure that it's odd. This is going to be super straightforward because you just take any random number, multiply by 2, and add 1. Then you get a random odd number. You square it. You open it. Everything looks the same so far. Let C be some square root of it, same. Let's define D to be this guy, which is, again, a square root of 1. So everything looks the same so far. But now the difference is that we have this mathematical theorem which says that if D is a square root of 1 modulo 2 to the k plus 2, then maybe D is not minus 1 or plus 1. But it's not so far from that. So it's minus 1 plus 1 or minus 1 plus 2 to the k plus 1 or plus 1 plus 2 to the k plus 1. In particular, if you take modulo 2 to the k plus 1 of D, then you end up with something that is indeed minus 1 or plus 1, because these guys here just go away. So that's what we do. That's the first bit in the modulus that we lose. We go from 2 to the k plus 2 to 2 to the k plus 1. So we get that in D is indeed between minus 1 and plus 1. And then finally, when you divide by 2, well, it turns out that you can divide by 2 if you know that the value is even. Like if you have an even value and you divide by 2, you lose 1 bit in the modulus, but you still can divide by 2. For this to work, all the parties they must have shares that are even, so that like every party can locally divide by 2. But because of the way that things are set up, this is indeed the case. So here, this division is actually possible, and this takes 1 bit from the exponent. So instead of being 2 to the k plus 1, it's 2 to the k. So that's why we have to start with 2 bits more. And with this, we end up with like a share bit, which is precisely what we needed. Now, why is this useful at all? As I mentioned, like it's a core primitive. We use it for a lot of things, and in particular, we use it for share conversions. So by share conversions, I mean like what you obtain in the previous protocol is a bit, but the shares are very large. The arithmetic values are super large. So what we want is like maybe to operate on smaller shares, like there are shares of a bit, but the shares are also smaller. So the way we do it is, I mean, to convert from arithmetic to binary, it turns out that there's something you can do local, and it's all fine. But you then need to go back to the original. So this is done by this. So to convert from binary to arithmetic, you sample a random bit, just like I showed before. And then this random bit, you convert it to binary, just like here. You use it as a mask to mask the bit that you want to convert. And now you can open this guy because like it's masked by this R. And then you undo the mask but with the other share, with the share you care about. So here I'm XORing B with R, and here I'm XORing it again, but now with arithmetic values. So now the share I end up with at the end is arithmetic. So we have share conversions. And that's very good because this allows you to compute binary circuits, but on binary shares instead of using arithmetic shares. And this is something I'm going to illustrate here with the bit decomposition protocol. So in the bit decomposition protocol, you have shares of some value, and you want to get shares of the bits of this value. This is pretty standard over fields. You just basically get a lot of shares of bits. You construct the value represented by these bits, it's just this guy. You use this R to mask X. You open the masked version of X. So far, so good. And now the thing that you usually do is that you undo the mask, but with a binary circuit. This is the standard way of doing it over fields. But here we can do something extra, something very nice, which is instead of undoing the mask, which means adding R to the bit decomposition of A, we first convert R to bits. So the circuit that we compute here, this binary circuit, which is public value, public bits, and this share value, it's very small. Like the shares are smaller because you're only sending binary shares instead of sending full arithmetic shares. And this is the main difference of this protocol with respect to other protocols. And then finally, you get shares of the bits, which you can convert to arithmetic shares if you need. So this is the main benefit of working over the ring is this particular line here, is that you can run the protocol over binary shares. All the other protocols follow the same template. So finally, I just want to discuss super quickly the implementation and benchmarks that we have. So again, it's Fresco framework, it's Java, and we can compare speeds and speeds to K in the same setup, which is, of course, very nice. And I would like to focus your attention on this particular column, which is the factor improvement between speeds to K and speeds. This particular table is for the online phase of just running a bunch of multiplications, like is the throughput, as many multiplications you can do per second, equality tests, and comparison. And the main point, and sigma here is the statistical security parameter, the main point is that we can get like a factor of roughly 5 improvement with respect to speeds. And this is very nice, and we conjecture, of course, that this comes from the improvement in local computation, but on top of that, we have less communication because of our smaller shares. This is about micro benchmarks, but again, as I mentioned, we also did some evaluations on support vector machines. So we see, again, we have a factor column here and a factor column here, and we see that the improvement actually goes between 2 up to 5 times roughly improvement. Where is this improvement coming from? Again, we can see that as the number of classes increase, the improvement also increase. And again, if you batch communication, so if you do several executions of the same model in parallel, it's actually better, the improvement. Why is that? The more number of classes you have, the more comparisons you have to run. So again, we have better comparisons protocols, so this indeed proves that, or this shows that having a better comparison protocol has an impact on this particular type of executions. Same for decision trees. The depth gets larger, the better the factor becomes, the depth, the factor. So again, like having a better comparison protocol indeed has an impact. And I did not mention anything about the preprocessing because speeds to K is not so good for the preprocessing, unfortunately. And this is because we have larger shares. So very quickly, red line is overdrive, the state of the art. Red line is speeds to K. So with a very slow network, or like with a one network, we have like we don't have a very good throughput. This is because like then the communication is the bound. Like you need to have your network bound, and you really want to have a protocol that's better in terms of communication. As the network becomes faster, we can see that if we have a 10 Gbps network, so a LAN, then you can actually catch overdrive because we are not network bound anymore. Then we can become communication bound. So to conclude, what we show here is an implementation, or we discuss an implementation of the speeds to K protocol, and also some practical primitives for computation over this type of rings. We saw that there is roughly a 5-fold improvement on the computation, on the running time, but also we saw, like I didn't mention this in the slides, but we have an 85-fold reduction in the communication costs. So again, we have circuits that are binary, so they are much faster. And as feature work, it would be nice, of course, to close the gap in the preprocessing. The preprocessing speeds to K is not so good, so it would be nice to close the gap here. And finally, we have all this set of tools, or this set of primitives that we would like to use. So of course, if anyone wants to think about any more applications of this is a great future line of research. With that, I conclude. Thank you so much.
Any questions? I have one question. Yep. So this, I consider your method of creating bits sort of like the method of roots, taking roots essentially. Does it generalize if you wanted to pick, let's say, instead of 1 or 2, like 1, 2, 3, or 1 to P or something like that by taking sort of, have you thought about that?
Yeah, so I guess a natural question is what for, first of all, but like even if you have like a clear application for that, I don't think it generalizes because this method requires like, I mean, you're using the sign, and the sign is like a binary thing, either negative or positive. So I'm not aware of any generalization of it. It may be the case that there is like a property that is not binary and you can use it, but I'm not sure that like you can do it easily. But it's an interesting question if you have an application for that.
Daniel Noble from University of Pennsylvania. Brief technical question. In your creation of the bit protocol,
yeah, sure.
How do you do the modding out by 2 to the k?
Yeah,
Are those?
I can only go back, so you have to describe again. Sorry, say again?
In your protocol for creating shares of bits,
yep.
In the last phase, so you have these 4 different square roots, and 2 of them have like this 2 to the k term, and so you mod out by 2 to the k. So how do you do the modding out by 2 to the k?
Right, okay. So our sharing scheme works in such a way that like, it's very nice, this property that when the part is locally like reduced, the effect is of reducing like the actual share. So if you want to take modulo something from the share, as long as it's a power of 2, then you can do it just by reducing locally.
Okay, thanks.
Okay, perfect.
Let's thank the speaker.